Hello students, in this video we'll study constant coefficient ordinary differential equations which have a quadratic factor. When solving constant coefficient ODEs, we factor to get linear terms these are terms of the form d minus a, and quadratic terms. And these terms are of the form d minus a squared plus b squared after completing the square. We know how to handle linear terms. D minus a y equals 0 is our essential ODE and can be solved as c1 e to the ax. But quadratic terms are different. Quadratic terms have two conjugate complex roots. Quadratic factors have two conjugate complex roots. We will write these roots as a plus ib and its complex conjugate, a minus ib. Recalling that to make a complex conjugate, we replace the coefficient of I with a negative. This implies that our quadratic term will have these two factors. The quadratic factor has the form d minus a plus ib and d minus a minus ib. Let's proceed with the algebraic foiling of this expression to get d squared, and then we'll have minus d a plus ib plus a minus ib, and finally plus a plus ib times a minus ib. If we look at the terms that are the coefficients of d, we see that this will simplify just to 2a, as the ib and the negative ib will cancel. And over here, we'll multiply a complex number by its conjugate, and we will see that this expression, after multiplying everything through, is a squared plus iab minus iab minus I squared b squared. But I squared is negative 1, so this entire expression is a squared plus b squared. Hence, our expression becomes d squared minus 2ad plus a squared plus b squared. We now realize this term is a perfect square, and we write this as d minus a squared plus b squared. Euler's formula will tell us that our quadratic term will be set to be 0 if and only if y is c1 e to the ax cosine of bx plus c2 e to the ax sine of bx. And this becomes our second essential ODE, which comes from Euler's formula. So let's see how we can apply this in an example. Let's solve y double prime minus 4y prime plus 20y equals 0. I will write this with our differential operator notation as d squared minus 4d plus 20 applied to y equals 0. And I'll complete the square on the inside. This is equivalent to d minus 4d, d squared of course, plus 4 plus 16, where I have completed the square, applied to y is 0. And this becomes d minus 2 squared plus 16 is 4 squared, applied to y is 0. Now using the Euler's formula relationship, we see that the general solution is c1 e to the 2x cosine of 4x plus c2 e to the 2x sine of 4x. And that is the solution of this example ODE. Thank you very much.